Hey, are you a ray of sunshine? Because every single one of your elements is glowing.
No, I'm actually an array of integers.
An array is a data structure that holds a fixed number of elements in a specific order. It's like a table of boxes where each box can hold a single element. To declare an array, we need to tell our code which type of data the array will hold and the length of the array, which is the number of boxes that it will have. Each position in the array is referred to by an index number, which starts counting from 0. This is something that often trips up beginners, since it's kind of weird that the first element is index 0 and the second element is index 1 and so on. But don't worry, you'll get used to things in computer science being kind of weird. It happens all the time. These index numbers can be used to both access and modify elements in certain positions of the array. This indexing ability is one of the biggest strengths of arrays because it gives them very fast random access. We're able to jump to any spot in the array pretty much instantaneously just by using the index number. Each array can only hold one type of data, so every one of its elements will have the same data type. For example, an integer array is only able to hold integers, and we can't put something like a string in there. This is called homogeneity. This may seem like a bit of an arbitrary limitation, like why is the computer telling me I can't let integers and strings live happily together under one roof? But there's actually a good reason for this. While we as humans recognize different data types as being completely different things, to a computer it's all just ones and zeros, binary digits.
Bits.
For example, the bit string 01000001 could either mean the integer 65 or the letter A. So the code needs to use types so it always knows how to properly interpret data. If we wanted arrays to be able to hold many different types, they would need to somehow store some additional information for each element that tells it which data type to interpret it as. But this would take up more space. It is much more useful for arrays to be simpler than that and to give the entire array a type to tell a computer how to interpret every element. So each array can only hold one type of data, but what's nice is that any valid type can be used inside of an array. Well, an array is also a type of data. So what if we were to put an array inside of an array? And now we have a two-dimensional array, an array where each element is also an array. These are often depicted as grids of data, where each element in the outer array is an entire row. It's perfectly legal to have all of these inner arrays have different lengths. This is called a jagged array, but many of the common use cases for 2D arrays have them all have the same length because this creates a perfect rectangle. We can access a single element in the 2D array by using two index numbers, first for the row and second for the column. This works because the first index number accesses one element of the array of arrays, so it gives back a one-dimensional array that represents an entire row. Then the second index number accesses a single element within this row. We could take this structure a step further by taking a bunch of 2D arrays and putting them in another array. Now we have a three-dimensional array. We could continue this pattern and add as many dimensions as we want, but I don't know how to animate a fourth-dimensional shape, so I'm just going to avoid that problem by moving on. Arrays have a fixed size, which means the length of the array can never change. It will always have the length that it was declared at. So if we completely fill up an array and we want to add another element, tough luck. There's just not enough room for this new element, so we'll need to overwrite one of the values already in the array if we want to get it in there. Or we can do some trickery with dynamic arrays, but I'll get to that later. To understand the reason why this fixed size limitation exists, we'll need to talk a little bit about how arrays work under the hood. When an array is declared, the computer reserves a chunk of memory that will serve as the array. The size of this chunk is the space that a single element takes up in memory multiplied by the length of the array. For example, if we want to create a 5-element integer array, this will take the size of an integer, which is 4 bytes in many systems, times 5. So the array will have 20 bytes of reserved space. So all of the data in an array is stored in a single continuous chunk of memory. This is called being stored contiguously. Indexing works by offsetting from the beginning of the array by the index number multiplied by the size of a single element. So if we access index 3 of the integer array, it goes 3 times 4 equals 12 bytes from the start of the array. This is actually why array indexing starts at 0, because the first element starts at 0 bytes offsetted from the beginning. The reason why arrays have to have fixed size is because the chunk of memory that is given to the array when it is declared is the only space that is reserved for the array in memory. All of the memory surrounding the array can be filled with important data that is used for other stuff in the computer. So we can't just expand the reserved array space because this could overwrite data that doesn't belong to the array. But what if we don't know how many elements need to be in the array? This puts us in a bit of a dilemma. We don't want to make it too small because then we risk running out of space. But we also don't want to just create a huge array to account for the possibility that we'll need a lot of room, because if we end up using barely any of that space, then the rest of the memory that we've reserved for the array is now being wasted. If only there was some way to dynamically grow the array to fit our needs. To get around the fixed size limitation of arrays, we can implement a data structure called a dynamic array. The general idea is that whenever we need more room in the array, we perform an operation called resizing to make more room. But of course, we just talked about how it's not possible to literally change the size of an array. What resizing actually is creating a whole new array with the desired size and copying every single element from the original into the new one. Then we can just use the new array in place of the original. So resizing an array isn't literally changing the size of a single array, but for the purposes of our code, once we implement a dynamic array, we can basically treat it as if it's an array that grows to fit our needs. But it's important to consider how much we should grow the array length by each time we perform the resize operation. We want to minimize how often we have to resize because copying every single element into the new array is pretty slow. Like, imagine if resizing always increased the length by 1. Once we exceeded the array size, we would need to make a new array, then copy into it. Then we want to add another element, we need to make a new array, then copy into it. One more element, new array, copy into it. The more elements we have, the slower this will get. So instead of growing the size by a constant number each time, we actually grow it by a factor, such as doubling the length every time we resize. This gives us more space to work with after each resizing, so we don't need to resize as often. So there still will be some wasted space with this sort of setup, but the fact that the array's length grows alongside the number of elements makes it much better than just choosing an arbitrarily large array size. And those are arrays. While we've gone somewhat in depth into how they work under the hood, arrays are actually pretty straightforward. They're simply fixed size collections of elements of a single type that can be accessed using indexing. It's crucial to understand arrays because they're super fundamental. Thanks to their simplicity, efficiency, and speed, they're the perfect candidate to use as a component or base for a bunch of other more complicated data structures. In fact, arrays are one of the 2 data structures from which all other data structures are built. So join me next time in this series to learn more about the other fundamental data structure, the linked list. Well, guess what? I'm also an integer array. You're exactly my type.
You seem very one-dimensional.